Okay, so let's say that we have a function f of q. Okay, now when you have function f, and you typically think of function as a one-dimensional thing, so x square, x cube, or q square, q cube, but f can actually be a vector, which means that it will have something like this: f1q, f2q, f3q, and so on till fmq. Okay, so this is a vector of functions. Each of those f's are scalars. So maybe the first f1 is q, f2 is q squared, f3 is q raised to 3, or it could be anything, e raised to q, whatever. Okay, so that's what f is. And then q here is, let's define q to be, q need not be a scalar either. So q can be, let's say, variables x1, x2, x3, so on, xn. So that itself is a function, is a vector. Okay, so now what we are interested in is computing this quantity, which is known as the Jacobian. It is the partial derivative of f with respect to q. So on top is a vector of dimension m. In the numerator is a vector of dimension m, and the denominator q has a vector of dimensions n. So when you want to do this calculation, what you need to do is you need to take each element of f and take the derivative with respect to each of the elements of q, and that is composed in this fashion. So it's df1 dx1. So you took this one and this one. Then you take df1 dx2. So you took f1 and then took the derivative with respect to x2, and keep doing that till you reach dfn dxn. So the first row is going to have only f1s, but the derivative with respect to x1, x2, x3, so on till xn. So the next row we have df2 dx1, df2 dx2, so on till df2 dxn. So we keep doing that, just keep continuing it with f3, f4, and so on, and eventually we'll end up with dfm dx1, dfm dx2, so on till dfm dxn. So you could just count the number of rows. So you can see here that the rows would be, well, there's f1, f2, fm. So clearly the number of rows are m. And then you can count the number of columns. The easiest way to count the number of columns is to look at here x1, x2, so on till xn. So there are n columns. So this Jacobian is a m cross n matrix. Okay, so it's sort of taking all combinations of f, all combinations of x, and taking the derivative. Okay, and it will soon be clear why this is important, but let's see how to do this calculation, so just to give you a hang of it. If you have f is x squared plus y squared, 2x plus 3y plus 5. Let's just move it to the next page. Yeah, so let's compute the Jacobian of this. Compute j equals df dq. Clearly, f here is f1, f2, which is going to be x squared plus y squared, 3x plus 2y. So 2x plus 3y plus 5. And then q is x and y. So the Jacobian is going to be df dq. Okay, so we have 2 cross 1 cross 2, and this is 1 cross 2. So what we expect is, since M is 2, N is 2, we'll have a 2 cross 2 Jacobian, right? So let's compute that. So I'll just write the formula. We have TF1, TX1. Oh, there is some internet problem. I think I lost. Oh, it's working here. That's good. Am I audible?
Yes.
Yeah, thanks. Okay, thanks for confirming. Seem to have lost internet on the other computers. I was worried that I may have lost internet here too. Okay, so here's the formula. df1 dx, df1 dy, df2 dx, df2 dy. Okay, the thing about partial derivative is when you take the partial derivative with respect to x, you treat y as constant. So if this is f1, when you take the derivative with respect to x, so we treat y as constant. So derivative of x squared is 2x. Derivative of y squared with respect to x is going to be 0 because y is treated as a constant. Then we have df1 dy. So we take this one with respect to y. So x is constant, so it'll be 0 for the first derivative. The second one would be 2y. Okay, so then we repeat it for f2. This is f2. Take the derivative of f2 with respect to x, treat y constant. So derivative of 2x is 2. And then we have df2 with respect to y. So we treat x as a constant. So so 2x plus 3y plus 5, derivative with respect to y is 3. And that is our derivative. Okay. Now you could also do this if he asks you to compute j at x equals 1, y equals 2. It's just a matter of putting the value of x and y. So 2, 4, 2, 3. Okay, it's very straightforward. Now, we're going to introduce a new thing here in Python to do this computation. There's something called a symbolic toolbox. It's very useful. What calculations are done by hand using variables can also be done using Python using the symbolic toolbox. Okay, so first of all, I load a new package. It's called sympy. Okay, so import sympy as sy. Now, if it does happen that you are not able to, you see like a tilde below it, it means that the package is not installed. You want to go to the terminal and type here pip python -m pip install sympy and enter, and then it will install the package for you. Now, I did not have to do that, but nevertheless, let's see what happens if you. So it says, let's go up. Okay, so it says requirement already satisfied, which means I already has sympy, so I don't have to install it. And this, the other thing which it gave was basically my pip is old, so it wants me to upgrade the pip. So pip is basically a command in Python which is used to install package. It says my pip is old. They have a 2.24.2 and f 23.01, but really it doesn't really matter. Okay, but if you want to upgrade that, you can just do the command they've shown here what to do. You should say, I think, Python install -- upgrade pip. Okay, so it's all installed. What I'm going to show you here is the same calculation we did by hand using the symbolic toolbox. So I define x squared plus y squared, 2x plus 3y plus 5. Okay, here that's basically a function whose derivative I'm going to find. Now, one thing you want to do is you want to tell before you use this function is that x and y are not numbers. They are symbolic variables. So that is done using this particular command. X comma y is symbols xy. Okay, if you don't do that, it'll throw an error. Okay, so that's just a comment, line number 9. F is fun x comma y. I sort of call that function, which will give me f1 and f2. Then I just do j equals f dot Jacobian z. So what is z? Z is x comma y. And then I tell it to print j, so that's a symbolic value. And then if I want to substitute 1 comma 2 inside j, then I basically do subs. I replace x with z0 zeros, that is the 1, and I replace y with z0 1, which is 2, and so it'll print jsim. So let's run this, and it should give the same output as the one which we got, hopefully. See. Okay, still computing. Okay, there it is. 2x, 2y for the first row, 2 comma 3 for the second one, same what we got here. And then if you sub in the value for x equals 1, y equals 2, you can see it's 2, 4, and 2, 3. Okay, so it works. So this is how you can do symbolic computations using Python. Okay, now let's move on. I'll show you some of the reasons or the applications of using the Jacobian. Okay, this is why it's useful. Why are we even studying this? So I'm going to show you 3 applications of using the Jacobian.